if I have like a lot of the zeros following a 1, this actually occurs, then I can say that the probability of this happening has to be like, if this is like 1 over 2 power of n, then the probability of this happening is like 1 over the same number. It's like 1 over 2 power of n. So I actually need like 2 power of n of the distinct elements has been inserted for this to actually occur. So that is the actual idea of hyperlog. It's just trying to compute what was the latest, what is the biggest number of this RA that has been inserted. If I'm seeing like 18, then probably there were about 2 power of 18 of distinct elements have actually been inserted. That's what the hyperlog algorithm is trying to do. And of course you can say it's like the range is like too large. 2 over 2 power of 15 and 2 power of 16, this gap is too large. So the log algorithm is trying to do like more estimate and trying to taking the mean of the actual elements being inserted, and the actual calculations is here. But I hope the above description kind of capture the spirit of what hyperlog is doing. So far, is it okay? We're all placed out? Yeah. So here I want to give like another aspect of what big data is. So big data doesn't mean that it's informative knowledge. Interesting information is often really small. For example, the visualization that I just showed, the actual information stored in there is so small that it can be computed into a browser. And for like the previous slide, I was showing that most of the big data computation is having like very, very small outputs, like the reporting, the internal reporting into a OLAP data store, and some of the ad hoc reporting, and finally the archives. Unless it's an archive, the normal output is really, really small. And sometimes it needs to further get compressed and finally get some interesting information. And hyperlog is one of the idea of this this information extraction. When you have like multiple data combined into one distinct kind, this is like you have a very large amount of data, but you only care about the final information that is like several kilobytes, and finally you only care about the integer number that is a distinct count. What if the extracted information is not a distinct count, it's something else? Is there some of the good algorithm that can extract some information that is even better than the distinct count? And actually, there's a lot of those. So here's a list of some of the streaming algorithms that can perform very similar to hyperlog. Those are all like data structures that can data flow through only once, and it can combine itself with some of the others. And then finally, you can ask it for some of the particular information. So count mean sketch and an improved version called count mean sketch. The first mean is the mean value, MEAN value, and then the minimized mean. Count mean sketch can do a frequency estimation of, for example, if there were some users string showing more frequently than the others, it can show this kind of distribution of those users. And there's an algorithm called DGIM. I hate those algorithms that's using the first letter of those authors. I can never remember those. But it can count bits in any time window. So if you want to count for some particular events that can happen from like minutely level all the way to like a yearly level, it can estimate this kind of count very fast. And also there are some of the other algorithms called like lossy count. It can count top k elements. There's a bunch of the top k elements estimates However, it's really hard to actually get a very precise top K estimate. Each of those has some of the strengths and weakness. So when you use those, survey enough to know what are the constraints for each of those. Yeah, some of those have 0 false positive. Some of those have like very minimal false positive, but each of those have their own properties. Yeah. And also there's the ASM, second order moment estimation. It can be used with a counting sketch, that is to estimate the if the data is being skewed. That is like some of the element has too much way higher count than the others. Then ASM is one of the streaming algorithms to estimate that. Yeah. And there's a particular one that I think everyone will love it. That is called BFR. Again, it's like 3 authors' name. And what it can do is it's a clustering algorithm that can be done in streaming fashion. So imagine you have a very high dimensional space, and you make a assumption that for the clusters, for each of the data points in those clusters that you want to estimate is a cluster, it's pretty much like a small ball. Like they are very close together and that is when you define it's a cluster. And to represent that cluster, you don't need to store all the points. You can actually only store the Gaussian distribution that can be calculated by the sum, count, the center of mass, and the sum of squares, that you can estimate like how large this cluster is. So when you string these algorithms, every time you when you see some of the points together, when those points are close enough, then you create like a Gaussian distribution that is only store the 4 things that I just mentioned: the center of mass, the sum, the count, and the sum of squares. And now you only need to store 4 numbers for infinite number of data points that can probably included into this cluster. And when you have 2 clusters that are close enough, then you merge the sum and count and those square of sums, and then this cluster just becomes a little bit larger. And since it has this kind of merge, or I say like more like a union operation in hyperlog log, all of those can be calculated in streaming fashion and can be done in MapReduce. That the actual calculation time is just log n. So I don't know how many of you have used the unsupervised machine learning, but most of unsupervised machine learning, you have O(n) squared complexity. But using this one with a strong assumption that the data that will be unioned into a cluster is basically represented by the Gaussian distribution, your actual computation cost is just log n, and it's significantly faster. Yeah. So a short summary of the probabilistic data algorithms is a lot of those are very scalable, and when those are the I don't know, like streaming algorithms, it can easily fit into MapReduce frameworks, and your actual complexity is just log n. And the accuracy, a lot of those algorithm paper, you can see how it's estimated accuracy, and you can finally decide like how many bits you want to store within each of the algorithms. And it can be, well, the last one maybe a little bit like, it's kind of like my vision. It's like if you implemented those into a SQL store, like Postgres or MySQL, then a lot of those calculations, since when you have those signatures, it doesn't really take a lot of space. But using the traditional MySQL store, you can store like way longer time, like way larger than what you can store into a browser. Yeah, and it can make a lot of the data visualization and like estimation even more flexible. Yeah. So I say this is a new era of online analytical platform, and also it's a new way to do some of the data science applications. And I feel like this is also a big next step for the big data industry, because of a lot of the big data engineering is more closely to what I just described in my previous presentation. That is, a lot of data engineering tasks doesn't really involve a lot of the data science stuff. And you can see from the tool chain, data science, what you usually use is R, Python, Pandas, or a lot of those like low memory usage tools, or I don't know, like small data tools, but it can do very complicated calculations. And on big data side, what you usually use as a tool is more like Hadoop, Pig, Hive. Some people try to use Spark. So far, the only two companies that I know really migrated into Spark are only two in production. A lot of the other companies at very large data scale, I didn't find many of them really succeed. Yeah, people did a lot of prototype, but it's just not that simple. Yeah, and I feel like the probability data structures is one of the key to combine those two. That can give you even more complicated applications available. Yeah. So here are some reference. I found one of the best book is Mining of Massive Data Sets, and they also have an online course. I think the new course is coming up in September. So any one of you are interested in those kind of data structure algorithms, it's a very nice place to start. And yeah, and another good book that has all, I think so far, all of the data streaming algorithms, it has a very nice reference. It's called Data Discovery from Data Stream. Yeah. Just before this book, a lot of the data streaming algorithms only exist in papers. But within this book, I found a lot of the streaming algorithms that I previously only found in papers. It has a collection of all of those. So it's also a very nice reference book. So yeah, questions? Disney 还有
APR 是台湾的 APR 吗？
对，
我们公司有在用。
跟你们的那个 CEO 聊到，然后他说你们有在用 Spark。
没有，我不是 APR 的。
哦，不是吗？
对，我是 V4。
OK。